All right, Pre-Cal, welcome back to, welcome back from your spring break. I hope you were as rested as I am. What we're going to start doing now is we're going to introduce the foundation of trigonometric identities. But the first thing that we want to do is we want you to understand like why you're going to learn it, why you need to memorize these things. So what I'm going to do is I'm going to kind of do a blast from the past. So you're going to have to bear with me because again, I'm teaching to you like hopefully you would be sitting in my room, and this is what I would definitely start with. So let's talk about why we need to memorize certain things, and again, I'm just going to remind you of a couple things. So we're going to talk about something that we previously talked about, and let's just look at, say, what if you were asked to graph y equals the natural log of e to the x? You know, you had options, right? I mean, some of you would be thinking right now, maybe you just break out a table. But when we did this, we learned some properties, right? Remember, we learned that if you had an exponent within a natural log or a logarithm, it could be moved out, which is what I did here. And again, there's just a reminder, like you learn that. You memorized that rule, that exponent could be moved out. Or if it was in a natural log, that exponent could be moved out. You learn that rule so it could be applicable, and it would take you here. You're like, all right, so now I have an equivalent expression. And so now what would I do here? So we would hopefully identify that you have the natural log of e, which is right here, which is 1. And then you'd be like, well, that's just x times 1. So technically the graph of the natural log of e to the x is going to equal the y equals x graph. And a much easier process and a much easier graph to establish if you understood those rules. So that's why we learned them. When we graphed this problem, it was much easier to demonstrate this graph than it was to be thinking about, well, what's that supposed to look like? Okay? So let's look at something else I asked you to memorize in semester 1. Let's get rid of that. I asked you to memorize what the parent function of, I think, what was there, 12 different parent functions that we memorized, and one of them was f of x equaling x to the third power. So what did that look like? Well, that looked like that. And why did we memorize that? Well, we memorized that because we really wanted to key off on what the end behavior was doing. So if I knew that anything to the third power was going to behave this way, right? We knew that as x approached positive infinity, the function approached positive infinity, rose forever. And as x approached negative infinity, well, the function also approached negative infinity. It fell forever. That's why we memorized that. We memorized that, so if I was asking you to graph this function, you could say to yourself, hey, it's third degree. I know what a third degree function is supposed to behave, at least on its end behavior, at least down here, that it was supposed to do this, and it's supposed to do that. That's why we memorized that. And then we went and did a bunch of other stuff with this. We found if you were to factor this, you'd say, hey, it's going to cross the x-axis. If I set this equal to 0, it crossed the x-axis at -1, get -2, get a -3, and we'd get something like that. So we're over halfway into the graph, and we haven't even broken out a table. Well, how would we get to this point if we knew something like this, right? So then we were like, well, hey, you plot at -3. Oops. You plot this at -3, you plot this at -2, you plot this at -1. You say, well, I know the end behavior is supposed to do this. Well, I knew that because I knew that. And the inside, the middle of the graph, well, it'd probably do something like that. And that's when we would bounce to a table. That one would become a little bit more monotonous. But our graphing experience got much more sped up by simply knowing certain things. Okay, so when I get into trigonometric identities, the first thing you're going to be thinking about is, why do I have to know these? Well, you're going to have to trust me, because they're at the very end of this. I'm going to give you an example, and at the end you're going to be like, whoa, okay. So I'm definitely going to want to know these foundation identities. And throughout this process, make sure that you're just pausing this, because you're going to want all these in your notes. Okay. So right now we have, what is a trigonometric identity? And there's a definition. A trigonometric identity is an equation that is true for all the values for the variable in which the expression is defined for. And that just simply means if there are no domain restrictions, well, that wouldn't count. Okay? And what I'm going to do is I'm going to show you, I'll tell you exactly the ones you need to write down, the ones you need to know by sight, and then periodically I'm going to give you a proof just to show you it works, just so you have some kind of idea. Just know that the proofs that I'm putting up here aren't something you're going to have to do every time. It's just to show you that they work, at least prove to you that the expressions are equivalent to each other. Okay? So the next thing we're going to do is we're going to talk about what are they. Now, the next slides are going to be the ones that you need to memorize. And when I say memorize, you need to know them so well that when you see it, you are thinking about what it equals. Okay? So let's start with the reciprocal identities. And make sure you pause this and write these down. Because these you have to know. You have to know, by heart. Okay, we need to know that the sine of x is equal to 1 over cosecant. Therefore, the cosecant of x is equal to 1 over sine. Cosine is equal to 1 over secant. The secant is equal to 1 over cosine. And the tangent is equal to 1 over cotangent. And cotangent is 1 over tangent. And the next slide will just take one of these, and I'll just show you how it works. At least how we know that these are to be true. Okay, so again, if you need to pause the video, go ahead and write those down. All right, so here's a proof. Now all I've done here is I've just generated a 30, 60, 90 triangle. We're very comfortable with the 30, 60. 30 looks at the 1, the hypotenuse is the 2, there technically should be a right angle right there. And the adjacent side of the 30 would be root 3. So let's look at an example here. If we said, well, what if, and remember, x is really equal to theta. So if x is 30 degrees? Well, the identity said that the sine of x is equal to 1 over cosecant. So that means that we would put the 30 degrees everywhere we saw an x, so we would start right here. A sine of 30 is therefore supposed to equal 1 over the cosecant of 30. Well, what's the sine of 30? Well, it's opposite, which is 1 over the hypotenuse, opposite of hypotenuse. The cosecant would be the hypotenuse over opposite. So all I've done is I put in the SOHCAHTOA here to remind you. And now I've jumped in here and I've thrown them in. So the sine of 30 was 1/2. And this is 1 over the cosecant of 30, so it's 1 over 2 over 1. And 1/2, or 1 divided by 2 over 1 is 1/2. 1/2 equals 1/2. It just shows that it works. You could do that for any angle. You could throw a 45, 45, 90 in there if you wanted to and just test it out. You could do this with all these trigonometric reciprocal identities, but again, it's only going to work on places where there wouldn't be a domain restriction. For instance, there wouldn't be a vertical asymptote in the graph. Okay? So what's the next two? The next two are called quotient identities, and there's only two. So there's only two quotient identities you must memorize. The first one is the tangent of x is equal to sine over cosine. We've got to know that, okay? We need to know that the tangent is sine over cosine. And the cotangent is just flip that. So the cotangent would equal cosine over sine. Remember what quotient means? Quotient means division. So we have a trigonometric word or a function is going to equal a fraction. Okay, so that's what quotient identity means. So for instance, if you are asked what is the tangent of x equal for reciprocal, that was the last slide, well, the tangent of x equals 1 over cotangent. If you were asked for the quotient identity, you'd have to say tangent is equal to sine over cosine. So again, the next slide, I'm going to take this information, and I'm just going to prove this one right here, again with another 30, 60, 90 triangle. Again, pause the slide if you need to write that down. Okay, so there's your 30, 60. And I just said, well, what if, in this case, x equaled 60 degrees? Well, again, we just put the 60 everywhere we see an x. And the quotient identity for tangent said the tangent of x equaled the sine of x over cosine of x. So the 60 is going to replace all my x's. So now the tangent of 60 is equal to the sine of 60 over the cosine of 60. And what I've done is I've just worked this out for you just so you could see it. Tangent was opposite over the hypotenuse. I'm sorry, tangent is opposite over adjacent. The sine is opposite over the hypotenuse. And the cosine is adjacent over the hypotenuse. And then I just took this information and I threw it in. Well, what was the tangent of 60? It was root 3 over 1. what is the sine of 60? Root 3 over 2, cosine of 60, 1/2. And we have a complex fraction here, so root 3 over 2 divided by 1/2 means we could flip that and multiply over here. So we have the root 3 over 1 is equal to root 3 over 2 times 2 over 1, and you can see that these 2's would have canceled, and we get that square root of 3 is equal to the square root of 3. Again, just to show that this does in fact work. Okay, now I have listed what we call Pythagorean identities. These are really, really important, like extremely important, especially when we get into the calculus realm and we do things called integration by trigonometric substitution. You're going to be using these things like crazy. So I've listed 3. I want you to know these are what I'm going to consider to be called the parent Pythagorean identities, and from these I'm going to generate 6 more, okay? So don't pause the video until we have written them all down. But these are the 3 foundational Pythagorean identities. We have the sine squared of x plus the cosine squared of x is always going to equal 1, just a single value, 1. And we have the tangent squared of x plus 1, that's going to equal secant squared. And 1 plus the cotangent squared is going to equal cosecant squared. Okay, so let's look at this one right here. So well, if this is true, and again, the next slide I'm going to prove this to you, be the last proof I show you. But if this is true, I should be able to take it and algebraically manipulate it to get a few other Pythagorean identities out of it. So let's just say that we wanted to take the sine squared of x and solve for it. And if you were just saying, well, if this is true, what's the sine squared of x equal? So let's write that down. What would the sine squared of x equal? Well, it would equal just taking this and subtracting over the cosine squared. So it would equal 1 minus the cosine squared. You're going to see that a lot. You're going to want to know that. And the same thing goes for, well, what if I wanted cosine squared? Well, what does cosine squared equal? I just take the sine squared and subtract it over. I'd get 1 minus sine squared. So these are the 3 that are going to come from this one. So you get the first one, and then the 2 algebraic manipulations. Okay? We're going to want to know all 3 of those. Same thing goes over here. I have the tangent squared of x plus 1 equaling secant squared. We're supposed to know that. But what if I wanted to know what is tangent squared of x equal? Well, we can just use some algebra by subtracting the 1 over. And the next one I'm going to show you is a little less prevalent. Probably could survive without knowing it, because sometimes it becomes a little bit more ambiguous. It would be looking at this just saying, well, what does 1 equal? Well, technically 1 equal that, but 1 is also going to equal taking the tangent and subtracting it over. This I will not test you on. I'm not going to test you on that one because 1 can equal a bunch of things. That just happens to be one of the things it can equal. Again, you can survive without knowing that last one right here. Okay, let's bounce over here and let's look at this one. 1 plus the cotangent squared is equal to cosecant squared. And again, what if we wanted to know what is cotangent squared of x equal? Well, we'll just take the 1 and subtract it over. We get cotangent squared of x is equal to cosecant squared minus 1. And you can see the same thing on that one. You could solve that one for 1 as well. So you have 3 different things that can equal 1, which is why it becomes a little less prevalent that we need to know this one. So this one you can also survive without knowing, but it's available for those of you that want to memorize all this stuff. You need to know this one. This one equals 1, you have to know that. You can survive without knowing these last 2 here. So these are the ones that you're going to want in your notes that you have absolutely and utterly memorized by sight, we need to know those. You can survive without those last two. Okay? So again, pause the video, make sure that you have these written down, and you haven't just written them down, you have written down Pythagorean identities, and then you've listed these. Okay? And just a side note, I don't want you to think that you could just write this down and not memorize these because you can use algebra to get them. Remember, the purpose of having these in your head is that you could look at any one of these versions and see it by sight. For instance, just simply look at sine squared plus cosine squared and think, oh, that's equal to 1. Or at any point in time in the near future, be able to look at the tangent squared of x plus 1 and say, hey, that's secant squared. You want to be able to know them that well. Okay, that's why I gave you that Quizlet over spring break to run through those flashcards. And if you haven't done that, you're gonna want to. Okay. Okay, so this was the proof I was talking about. Only reason I'm giving this to you is because there's a math property here that you may not have been aware of. So we had the sine, it was the sine squared of x. Remember, x is theta, so you can have thetas or x's in there. So here's a Pythagorean identity. It says the sine squared of theta, the sine squared of x plus cosine squared of x is equal to 1. And we're saying, well, what if we set x or theta equal, what did I do here? 30 degrees. That means I was going to put a 30 degree here, put a 30 degree here. But here's the property you may not have known. Anytime we have an exponent assigned to a trig function, we can take the exponent and we can move it out, which is what I've done here. Instead of writing the sine squared of theta, I wrote the sine of theta squared. I did the same thing to cosine squared of theta. I wrote it as cosine theta squared. I moved this out, here and here. Now I threw in the 30. So now I have the sine of 30, which I know, and so do you, squared, and I have the cosine of 30 squared. So what was the sine of 30? What was 1/2? So I've got the 1/2 squared. Cosine of 30, again, you could look over there, adjacent over the hypotenuse, root 3 over 2. Now it's root 3 over 2 squared. Well, square 1/2, what do you get? 1/4. Square root 3 over 2. You square a square root, the square roots cancel. You get 3, and square the 2, you get 4. Now I have 1/4 plus 3/4 was supposed to equal 1, and of course 1 does equal 1. So there's the proof of, again, just grabbing a 30, 60, 90, using some values to make sense of this identity. Okay? Now the last set I'm going to give you here is the last ones I'm going to ask you to memorize by sight. And they are called odd and even trigonometric identities. I'm going to help you with a little trick of how you can memorize these so they're just a little bit faster. But the first thing I want you to do, and again, I'm not going to give you a proof here because the proofs are actually relevant to their graphs. All an odd identity means is it was reflective, there was a reflection across the origin. Means these graphs are all reflections across the origin, and if it was an even function, it was a reflection across the y-axis. You may not have remembered that back to your Algebra 2 days, but that's what an even and an odd function represented. Odd was simply it was reflective across the origin, and an even function was reflection across the y-axis. Okay, so that's what it's talking about here. Now, notice the similarity here is that we all start with the sine, the cosecant, the tangent, the cotangent, and even over here, the cosine and the secant of a negative angle. So, for instance, the sine of negative 30. So, what it says is in an odd function is if you're taking the sine, the cosecant, the tangent, or the cotangent of a negative angle, the negative can be brought out front, which was written right there. So, for instance, the sine of negative 30 degrees would equal negative sine of 30. Again, you can prove that. It's true. It works. So for all odd functions, the negative can simply be brought out front, and it would be an equivalent expression. What the even says is, just notice what happens with the even. The even says that the negative simply is disregarded. So basically it was saying over here that the cosine of negative 30, well, that would equal the cosine of 30. Now, I will real quick just generate that over here just so you can at least grasp onto that proof. Remember what a negative angle did in previous chapters. A negative angle was indicative that we were taking an angle and we were going clockwise. So for instance, if we had an angle of negative 30, it would have ended up here, going that way. So that could have been negative 30 degrees. And what quadrant are we in? We're in quadrant 4, right? All students take calculus, and in quadrant 4, cosine was supposed to be what? Positive. So that's why this is working, that this cosine of this negative angle was going to equal the cosine of its positive angle. And that could have been why. That is the why. It's definitely one of the reasons of how you can generate a proof. But what we want to know here is just that you could look at these words, that you could look at these expressions, and you can come up with this equivalent. And the easiest way to remember it is remember these two. Remember for cosine and secant, because those are connected to each other, right? They're reciprocals of each other. Cosine and secant, the negative is disregarded. Therefore, all the other functions, the negative is brought out front. So if you know these two, for cosine and secant, just disregard the negative. You'll know that the rest of them, you will not disregard the negative, and you'll put a negative in front of it. Easiest way to remember those. At least it was the easiest way for me. Okay, so again, pause the video, make sure you have these down. Again, we want to know these by sight. We want to know them by heart. Now what I'm going to do on the next slide, and the very last one I'm going to do here, is I'm going to demonstrate why would we want to know these. Okay, an example of this type of problem. When we start dealing with trigonometric functions, or identities, we're going to start with what is called simplify. So here's an application of why we need to know these things. So let's just say that we've got a problem that simply says, hey, simplify this thing. And first of all, what simplify means is we're going to take this thing that's fairly messy and we're going to break it into the lowest and most reduced form we can get. And we know we're going to be done when the only thing to do is to continually or make it even messier. So we've got to get to the lowest point. Oftentimes it's a number or a single word. So right now I've got the tangent of x times the sine of x plus cosine. We're asked to simplify this. So this is why we need to know the identities so well. We're supposed to look at this and start running through our head of the things we know about each and every one of these. For instance, I could see sine, and if I knew my reciprocals, and you knew your reciprocals so well, you may be thinking, well, sine's 1 over cosecant. And then you would look at it and go, is that something I should do? Well, tangent and cosecant are not very compatible. So even though it's an identity, it's not something I'm going to use here. What I'm going to do is I'm going to look at tangent and say, hey, I know it's quotient identity. Tangent is sine over cosine. All I've done is I've simply changed this to this. Everything else just fell. Now the reason I would do that is because I was thinking ahead, right? You're almost playing chess with this. It's a puzzle. If I turn tangent to sine over cosine, I'm going to end up with a tangent times a tangent, which is my next step. I'm just simply going to multiply those together. And I'm going to treat sine times sine just like I would treat x times x. And I'm going to get sine squared x over cosine. So all I did was I combined those to get that next step. Now, again, this is going to be very difficult in the beginning, but hopefully it becomes a little bit more of a challenge and you start to enjoy these. The thing is, now I'm thinking mathematically. Hardest part is I'm thinking mathematically with words. And I see a fraction plus something that is currently not written in fraction form. So if I thought about it in fraction form, what's it missing? Well, it's missing a common denominator. And remember how I've always done this? Common denominator has to be cosine. So I can multiply that up right there. I can multiply that up right there. Multiply those together, just like I always show that. If I do that, I'm going to get that. Sine squared times 1 is sine squared. Cosine times cosine, cosine squared. Cosine times 1, cosine. So there's my common denominator. Well, why would we need a Pythagorean identity? Look at your list for Pythagorean identities and tell me what the sine squared of x plus cosine squared of x is supposed to equal. Well, it equals 1. This is a Pythagorean identity. This is why we want to know them so well. So I could just say, hey, that's a 1. So I'm going to put that over there. So all I did was take sine squared plus cosine squared, and I made it 1. Now it's 1 over cosine. Now look at your list. The very first list you wrote in your notes, reciprocal identities. What does 1 over cosine equal? Secant. I have taken an expression that was fairly messy, and I've converted it to one word. These equal each other. There's no way in the world you're ever going to memorize all the identities. We do, in fact, want to know the foundation identities, so we can take something we don't know, and we can start chipping away at it to get to something that's much smaller and more condensed and reduced. So again, this is where we're headed. Matter of fact, my next several videos are going to be taking trigonometric identities and using them in the simplification process. So again, this was just the final one to show you why you need to know the foundation identities so well. So we can start with a problem like this and we can start working through it. Now, what you're going to want to do in the beginning is you're going to want to have that list next to you, okay? You want to have it as a reference piece of material, but when we get into day 2 and 3 of doing this, you don't want to have to be looking at that. It's far too time consuming. You want to know them so well that you can look at it and you can start thinking ahead in the problem. Hey, I want to do this because this is going to be helpful. Okay, so that's where we're headed, and that's your video for the day. Good job.